Here we go with example 4. So we have directions that say how many terms are there in each of the following sequences. So we have 4 different examples, and our first one is 51, 52, 53, 54, so on and so on, up to 251. Okay, so is that one of those special types of sequences that we've seen already? Which one? This one would be an arithmetic sequence because we're going up, we're adding 1 to get from each term to the next term. So that means it has a common difference of 1. So if this is arithmetic, then we had a formula because I mean, you could, if you wanted to, you could continue writing out all of the terms until you got to 251 and then count up and see which actual, what the n was, which term it actually was. But that would be just monstrous to try to write all of those terms out. So my suggestion would be to use the formulas that go along with the arithmetic and the geometric sequences. Okay, so I'm going to ask you to pause for just a minute, and I want you to go through and think about each one of these examples or each one of these problems and see if you can figure out how many terms there are in each one of these sequences. See if you can come up with a plan, and then when you're done, or if you get frustrated, then go ahead and push play again, and we'll go through each one together. Okay, go ahead and pause now. Okay, so how did you do? I hope you did really well. I hope you figured it out, but if not, don't feel bad. We're going to go through each one of these so that you can see what I would do in order to approach these problems. Okay, so like I said, with this first one, we are going up by 1 each time. So we know that we have a common difference of 251. I mean, no, 251 of 1. So we know we have a common difference of 1. We know our first term, A, which is 51. What we don't know is what is n. How many terms, or, which term is this one that turns out to be 251? Well, for that, we do have a formula. That formula that says a sub n equals a plus n minus 1 in parentheses times d. So we do know that last term that we're dealing with is 251 equals a, our first term we said was 51, plus n we don't know, and d we know to be 1. So now we can solve for n, and that will tell us what the 251, which term that is. So let's see, if I subtract 51 from both sides to begin with, or you could distribute the 1 first. Either way, it doesn't matter. But if I subtract the 51 from both sides, I get 200 equals n minus 1 times 1. And then if I distribute the 1, I get 200 equals n minus 1. And then if I add 1 to both sides, we get n equals 201. So that tells us that 251 is the 201st term in that sequence. So I hope you guys did really well with that one. All right, let's try the second one. This one might have been a little bit more challenging. So we have 1, 2, 2 to the third, or 2 squared, 2 to the third, on and on up to 2 to the 60th. Okay, so the first thing we need to figure out here is this arithmetic or is it geometric? Because that's going to tell us what formula that we need to use along with this. We are multiplying by the same thing to get from term to term to term. Did you figure out what that was? To multiply, you would multiply 1 times 2 to get 2. 2 times 2 would be 2 squared. Times 2 would be 2 cubed, and so on and so forth. So our r here is 2. And we know our a is 1, so we have enough information to figure out what is the number of that term. Which term is it? So if we say, okay, 2 to the 60th will equal a, which is 1, times r, which is 2, to the n minus 1 power. Well, 1 times anything is itself. So that means 2 to the 60th equals 2 to the n minus 1. Now, I don't know if you remember this. You might have gotten stuck at this point, but we had when you were working in college algebra, we had a rule that said if the bases are the same, the exponents must equal each other, because the only way that 2 to the 60th equals 2 to this is if this whole thing happens to be 60 also. So those exponents have to equal each other. That means 60 has to equal n minus 1. And then if we add 1 to both sides, we get n equals 61. So that tells us that 2 to the 60th is the 61st term in that sequence. All right, what about the next one? The next one is 10, 20, 30, 40, on and on and on, up to 2,000. So did you figure out that this was an arithmetic sequence to start with? Hopefully. And what are we going up by each time? We're going up by 10. We're adding 10 to get from term to term to term. And we know our first term is 10 also, so we have enough to be able to use our formula. So our formula again is a sub n equals a plus n minus 1 times d. So I'm going to use 2,000 for my a sub n equals a, which is 10, plus n minus 1, we don't know what n is, times d, which is 10. Alright, so if I subtract 10 from both sides, I get what? 1990 equals n minus 1 times 10, or we could have distributed that out first. Either way, doesn't matter. But then if we distribute it now, we get 1990 equals 10n minus 10. So if we add 10 to both sides now, we get 2,000 equals 10n, and then dividing both sides by 10, we get n equals 200. So that tells us that 2,000 is the 200th term in that sequence. That'd be writing out a lot of numbers to get that. Alright, and then lastly, here we have 1, 2, 4, 8, 16, 32, on and on and on to 1024. So did you figure out that this was a geometric sequence? It absolutely is. And what are you multiplying by in order to get from term to term to term? It looks like you're multiplying by 2. Absolutely. And we have our a term, so we have everything we need for our formula. Remember, for geometric, it's a sub n equals a times r to the n minus 1 power. So a sub n in this case is 1024 equals a is 1 times r is 2 to the n minus 1 power. Alright, so 1 times anything is itself. So we have 1024 equals 2 to the n minus 1 power. And remember that problem that we did a while ago, we said if the bases were the same, then the exponents had to equal each other. So is 1024. Can I rewrite that as 2 to some power? You may have to play a little bit on the calculator to figure that out, but it actually is. It is 2 to the 10th power. So 2 to the 10th would equal 2 to the n minus 1, and now we have the same base, which means the exponents have to equal each other. So 10 has to equal n minus 1. So if I added 1 to both sides, I would get n equals 11. So that means that 1024 is the 11th term in that sequence.